Hello everybody, it's Doug here. In this video, which is part 1 of a 2-part series, I'm going to take you through the design and fabrication of the 3 steel components in the tremolo system of Brian May's original Red Special guitar. Part 2 will cover the installation, operation, and comparison with a professionally made hardware set. Brian and his father Harold conceived this ingenious design comprising a pivoting vertical tailpiece to mount the strings and a static section of plate mounted horizontally, flush with the top of the guitar body. Its protruding edge is fashioned into a point to act as a fulcrum. String tension is counteracted by the compression force of 2 springs, which abut the rocker block. The moving components are held in position with 2 set screws, themselves anchored into a section of steel bar held captive within the body. Spring tension can be adjusted by inserting a flat blade screwdriver through holes in the back of the guitar body. Knife-edge pivot bearings are a basic mechanical engineering concept and are typically deployed in weighing balance apparatus. They're also ideal for pendulum clocks, as with this example built by a user on the National Association of Watch and Clock Collectors Forum. Leo Fender's 2-post floating tremolo patent, filed in August 1954, operates on this principle, and it's likely that Harold May reviewed this design and considered that it could be improved by extending the bearing edge to the full width of the string cowling and mounting the springs in line with the block. Because of the placement of the springs relative to the rocker and their heavy-duty specification, the Red Special's tremolo system allows a large range of downward movement, allowing Brian to make a range of dramatic and unearthly pitch variations he describes as aeroplane noises, whale noises, dive bombs, and eerie screeches. In the main part of the video, I'll discuss the design of each component in the assembly, illustrated by CAD drawings and 3D renders. Then I'll show you how I made each one. My YouTube videos cover a wide range of topics related to Brian May's musical equipment, and further information on all my projects is available on my website, dsgb.net. Please support my work by liking, commenting and subscribing here on YouTube, and follow me on social media platforms including Facebook, Instagram and Pinterest. I've sourced 3 sections of gauge plate, or ground flat stock, in imperial dimensions, 5/16 inch thick by 1/2 inch high for the set screw mounting block, 1/8 inch thick by 1.5 inch wide for the knife edge bearing plate, and 5/16 inch thick by 1.25 inch wide for the rocker block tailpiece. Each piece is 18 inches long and is formed from tool steel, which is a hard, tough and wear-resistant grade of steel with a carbon and alloy composition. You can see some details on this on the package label. I'll use a variety of equipment to make the components, ranging from basic hand tools, such as a hacksaw, through hand-operated power tools, such as an angle grinder, to my CNC machine as a rotary multi-tool for precision cutting and grinding operations. I'll also make extensive use of my mini drill press and an engineering vise for the drilling operations. Let's begin with the simplest and easiest component to make, the set screw retaining bar. The Red Special tremolo system is mounted with 2 self-color 1/4 inch UNF thread hex head set screws 2 3/4 inches long. These screw into a section of steel bar held captive between the guitar body sections, with 1/8 inch rebated into the lower section and 3/8 of an inch in the upper section. I've seen some tremolo systems in which this component is an unnecessarily thick piece of metal. However, it's likely that Brian would have made this from the same 5/16 inch thick steel plate as the rocker block tailpiece. The retaining bar is just visible in this X-ray image, and it does appear to be 5/16 inch thick and the full width of the knife edge bearing plate. First, I measure and mark the desired length of 2 3/8 inches or 60 millimeters using digital vernier calipers. Next, I mount the short length of steel bar in a vise and cut it to approximately the correct size using an angle grinder with a thin 1.2mm aluminium oxide cut-off disc. With the vise now mounted to the drill press bed, I next use a small diamond-coated cutting disc intended for use with rotary multi-tools to dress and hone the cut edge to the desired length. I try to work to within 0.1 to 0.2mm accuracy, even though the exact width isn't important, because the rebates in the oak sections can be made to fit the actual component dimension and ensure that it is centered correctly. Working accurately might not always be strictly necessary, but it often helps avoid additional work later in the process. Next, I mark up the horizontal and vertical center lines of the screw holes by scoring again with the caliper jaws. Then I mount the cut section face up in the vise and ensure that it is level. I use a 1mm twist drill to locate the drilling position accurately, and then insert a 5.5mm diameter twist drill to drill the pilot hole. I've found that spending the extra money to buy tungsten carbide twist drills in a few specific diameters pays dividends by making the drilling more efficient and because they tend to be more durable than standard high-speed steel versions. When the pilot hole has been drilled, I tap a 1/4" UNF thread with a 3-piece tap set, applying an aerosol-based light lubricant regularly. If you've never attempted these operations before and would like some guidance on how to tap threads in metal manually, there will undoubtedly be many professional instructional videos here on YouTube. I'm not proficient at this, but I've learned that the best results are obtained by using the drill press as a guide to maintain alignment, mimicking the sequence of operations that a machine operator using a manual or CNC lathe would follow. Visually examining the finished component, everything appears to be satisfactory. I've test fitted the set screws and they fit securely and they're aligned with the horizontal and vertical axes, so we're off to a good start. Next, we step up a bit in complexity with the knife edge bearing plate. This is fashioned from a section of 1/8" thick steel plate, measuring 2 3/8" wide by 1.5 inches long. The fulcrum is formed by grinding a 60-degree angle into the forward edge, and it has 5 countersunk screw holes to mount it flush with the surface of the oak block in the upper section of the guitar body. Although 5 number 10 by 1.25" countersunk slotted wood screws would likely be adequate for fixing this plate, Brian and Harold decided to increase structural integrity by anchoring the upper and lower sections using 2 1.5" long countersunk set screws, possibly 2 BA or 3/16" BSF thread, into 2 1-inch diameter penny washers. I'll demonstrate and discuss this setup in more detail in the follow-up video, part 2, where I'll mount the hardware I'm making for this video in a test jig which replicates the assembly in the original guitar. For the initial preparation of the workpiece, I follow the same process as with the set screw mounting bar by clamping the section of steel bar in a vise, cutting it to approximately the correct size using the angle grinder. Then I hone the cut edge by passing the diamond-coated cutting disc over it several times. I mark out the center lines of each of the 5 screw holes by scoring with the measuring calipers as before, align the drill press chuck in the correct position using the 1mm twist drill, then I switch to a 3/16" diameter tungsten carbide twist drill to drill the hole to accommodate the number 10 wood screw thread. A test fit of a stainless steel number 10 wood screw indicates that I do need a little bit more clearance on the threads, so I'll increase the hole diameter using a 5mm drill. A quick pass through with the drill bits and then a recheck, and we're good to proceed. A 23/64" 9.1mm high-speed steel twist drill is required to form the countersink for these screws. These larger diameter imperial-sized HSS twist drills tend to be too long for my mini drill press, so I usually have to remove a section of the plane shaft before I can use them. I continue to drill the countersink and judge the depth of the screw head lip by eye. I clean up and again test fit a screw. This looks satisfactory, so I'll repeat the process 4 more times. The marquetry veneer is glued directly over the knife edge bearing plate, so any protrusion will need to be dressed by milling or filing. If the screw heads sit too low, the gap must be filled with either wood filler or epoxy resin, then abraded flush. I remove the plate from the vise and visually inspect it. Everything seems to be in order, so we'll move on to forming the 60-degree angle on one long edge. Hopefully it's self-evident that the knife edge requires to be ground precisely to ensure that the bearing alignment is correct and there's no unwanted movement during use. To ensure that this operation is executed to a high standard, and because I don't own a precision tilting metalworking vise, I decided to make a mounting jig by CNC milling a V-slot in a hardwood block offcut. This is straightforward to design because I've already created the objects in a CAD software utility. When the wooden block has been milled, I screw the knife edge bearing plate onto it, taking care to ensure that the edge is aligned to the machine bed in the XZ plane. I grind the 30-degree angle on each side by manually passing a small diameter diamond-coated grinding burr over it. This is intended for use in rotary multi-tools, for light-duty grinding and sharpening tasks, and the CNC machine itself isn't designed for heavy-duty milling of metals, so I take care here. I only remove 0.05mm per pass, and I complete several passes at each Z position, while listening for the resistance reducing before decrementing the grinding burr. Inspecting the finished component, this approach appears to have been successful, which is a relief because this was the first process in the overall sequence that I was concerned might not execute satisfactorily. Let's move on now to the most intricate component in the system, the rocker block tailpiece. The moving component of the tremolo assembly is fashioned from a section of steel bar 5/16 inch or 8mm thick. The other dimensions are approximately 1 1/4 inch or 32mm high and 3.5 inches or 89mm wide. The string ball ends are contained by a 2 3/8 inch wide cowling to accommodate a 2-inch string spacing. 2 holes are drilled at a 1-inch spacing to allow the mounting bolts to pass through with sufficient vertical clearance. These holes appear to be between 7/16 inch and a 1/2 inch diameter on the original item, but I'll be making these smaller, 3/8 of an inch, as I'll explain soon. 2 blocks with a full height 3/16 inch vertical thread are screwed onto each side to allow an articulating tremolo arm to be mounted. A 90-degree V-shaped groove is milled along the lower part of the string cowling to form the mating surface of the knife edge bearing. The square section on top of the string cowling and the edges of the side blocks have been rounded off. I follow the same process as with the other 2 components, marking out the desired width using vernier calipers, cutting the metal bar roughly to size using the angle grinder with a thin cut-off disc, and then honing the cut edge using the diamond-coated cutting disc. Throughout this project, I have batched all the cutting operations in one sequence and all the drilling operations into another sequence to try to be as process efficient as possible. Working only in my spare time during evenings and weekend afternoons over several weeks, being organised helps to minimise frustration. Next, I mark out the cutouts to form the string cowling. The side pieces are 7/16 of an inch high and approximately 3/8 of an inch wide. I considered using the angle grinder to save time and effort here, but ultimately I decided to trade greater control for time saving and use a combination of hand tools to achieve the cuts. I start off the grooves with the thin diamond-coated cutting disc mounted in my Bosch Professional rotary multi-tool, and then I switch to a hacksaw. I upgraded my junior hacksaw to a quality full-size version with a 300mm long blade because junior hacksaw blades are generally not fit for purpose to cut hardened steel. Well, that's the basic shape of the rocker block tailpiece cut out, and I've done some light dressing with metal files. Next, I score the centre lines for the holes that the set screws pass through. I place the steel block face up in the engineering vice jaws and drill 3/8 inch diameter holes in 3 stages with successively larger twist drills. I find that the tungsten carbide twist drills bite more readily than the high-speed steel versions, and then progress through the bulk material more efficiently. So I start here using 2 of my newer, sharper drills, firstly 3/16 of an inch, then 6.5mm, then the 3/8 inch drill, which is high-speed steel. I don't know for certain the diameter of the holes on the original component, possibly 7/16 of an inch to 1/2 an inch, but the chuck on my mini drill press has a maximum jaw opening of 10mm, so that practically limits my ability to drill larger holes in any case. Let's take the opportunity to discuss the springs. These were the inner valve springs from a vintage 1928 Panther motorcycle. This has been verified by Mark Reynolds, who has also obtained a set, and thank you Mark for many useful discussions while making this video. The specifications are displayed on the screen now. Logically, there's no reason to make the pass-through holes in the rocker block any larger than the inner diameter of the spring coil, which is around 11.5mm. They can be smaller, but there must be sufficient vertical clearance when the tremolo is operated. This is what the rocker block tailpiece looks like at this stage, with the string ball end retaining cowl shape formed and the set screw pass-through holes drilled. Next, I mark out, drill and tap the vertical threads in both flanks of the block for the tremolo arm mounting post. The original is most likely 3/16 of an inch UNF thread, but I have a large metric tap and die set, and I can't justify buying a separate imperial set for this project or future work, so 5mm is my choice here. I drill a 4.2mm diameter through hole with a solid carbide tap drill, then, as with the set screw retaining block, I use the drill press chuck as a tapping guide and manually rotate and carefully lower it as the tap bites into the metal. A test fit of the block with the Tremolo arm assembly from the RS Mods hardware kit indicates that the thread has been tapped satisfactorily. Moving on to the more challenging aspects of the fabrication sequence, I approach forming the string ball-end retaining cowl with two operations, drilling and milling. Firstly, I mark out the center line of the hole, which is off-center. I made slow but steady progress with this 60mm long hole by swapping drill duty several times throughout, using newer, sharper, smaller diameter drills to cut into the metal, and then opening out the hole with a 5mm drill. String ball ends are generally 5/32 inch or 4mm diameter, so the cowl inner diameter shouldn't need to be wider than 3/16 inch or 5mm. My drill press and chunky metalworking vise significantly limit the clearance height, as does the flute length on my 3/16 inch twist drill, so this process was somewhat frustrating. Removing the block from the vise and examining the hole, thankfully it seems to have drilled exactly as I intended. I deploy the same method I used to grind the knife edge bearing plate and CNC mill a V-shaped slot in a softwood offcut block. My CAD design shows that the rocker block tailpiece needs to be mounted at 34.6 degrees to the vertical to accurately form the angled surface from the rear edge to the apex of the cylinder that I've just drilled. I use a 32mm diameter reinforced alumina cutting disc from my rotary multi-tool set to grind the metal. For the reasons I stated earlier, I stepped the CNC machine spindle manually at only 0.05mm per vertical pass, using multiple passes until I hear the cutter engagement reduce before advancing. When the lower cut is complete, I make a second pass to remove the metal strip, and then some honing passes along the upper edge. In retrospect, I should have manually shaped this region with metal files, because I cut too far into the cowl, and the outcome isn't consistent either with my design or the original guitar. Nevertheless, there is still sufficient material remaining on the upper part of the cowl to allow the 90-degree edges to be rounded over. Given how much scope there is for any of these operations to have gone wrong, I'm very satisfied with the outcome at this stage. Next up in the sequence is drilling the string pass-through holes. I carefully measure and mark out the center lines at spacings of 2/5 of an inch or 10.16mm. Although I'm trying to find the simplest method of executing each operation with the tools and equipment I own, this has been a long project and summit fever does creep in a bit at this stage. Rather than making a wedge or a mounting block, I judge that the metal workpiece should be held securely enough between the vise jaws during this low-force drilling sequence. Thankfully, this proves to be the case, and I judge the 10-degree angle by eye with reference to a printed copy of my CAD drawing. A 2mm diameter hole, equivalent to 5/64 inch imperial, will offer sufficient clearance for all 6 strings to pass through. Note that the 2 holes for the largest wound strings are larger, possibly 3/32 inch on the original Red Special. I only have metric high-speed steel twist drills and a 1/16 inch tungsten carbide drill, so I decide to start the holes off with the smaller carbide drill and then open them out to 2mm using the HSS drill. I quickly realise that the drills flex and slip with the full flute length exposed, so I overcome this by inserting them further into the chuck. Okay, it looks like drilling these small diameter holes has executed satisfactorily, so I move on to the final machining operation, that is, milling the 90-degree V-groove in the forward face of the block. To mill the mating surface for the knife edge bearing, I need a tungsten carbide cutter with sharp pointed 90-degree flutes. I score in the line for the groove, which is 1/32 inch or 0.8mm deep. Then I start milling using a small engraving cutter. I then move to a 6mm diameter spotting drill and follow the same procedure, making low-depth passes traversing the CNC machine spindle. I try this with and without lubricant. The end result is satisfactory, but the cut isn't as clean as could have been achieved with a milling machine designed for heavy-duty metalworking, which would have had no free play in its cutting head. I probably could have achieved a cleaner result using my drill press, but would likely have ended up with repetitive strain injury in my wrist. All that remains now is the manual rounding over of the 90-degree angles on the upper front edge of the string ball end cowl and the side wings. This isn't necessary for function, but yields a more pleasing aesthetic appearance, especially on the visible parts of the component. I'll use metal files on the sides, which will not be visible in use, but I decide to proceed more carefully on the cowl and use 120 grit 3M Stick-It Gold abrasive paper, both mounted here on an aluminium block for the initial cut and also as a free strip. To give myself more clearance on the workbench, I avoid the obvious solution of mounting the workpiece in my vise, and instead screw it onto a strip of softwood, which I clamp to the surface. I'm aiming for a roundover radius of around 2 to 2.5mm, but I stop when this looks satisfactory to my eye. For the side edges, I use the same mounting method, but with a larger softwood block, and I start with a metal file, aiming for a 4mm radius curve. When I've removed sufficient metal, I finish using 120 grit abrasive paper strips. I allowed myself to be a bit more aggressive with this operation, and it paid dividends because I was able to achieve a satisfactory roundover in a much shorter timescale than I originally anticipated. I think I've shown you quite enough drilling, cutting, milling, grinding, filing, and sanding operations for one video, so I'll bring this to a conclusion here while we examine the edge roundover work. To finish these pieces, I still need to complete some final shaping with the metal files and surface dressing with finer abrasive papers. Moving down through 320 grit, then 600 grit, to remove unsightly machining marks, leaves the results shown in these images. Well, that's all for this first video in this series. I hope that you found my approach to the design and fabrication of the metal components in Brian May's Red Special guitar tremolo system informative and helpful if you're considering whether to make your own set or buy one from a commercial supplier. In part 2, I'll cover the installation, operation, and comparison with a professionally made hardware set, this Relic hardware kit provided by RS Mods in the UK.